With this, so far we have created a shift register which is sequential. Means it basically takes a clock input, and based on the clock edge, this shift register can load a parallel bits or scan in, scan out kind of serial shifting and bit operations, and can have shift in both direction. But the heart of this implementation is those flip flop, which essentially operates on the clock edge. So that means, let's say I have a 32-bit shift register in this way, and I want to shift for 10 bits. So that means I need to wait for 10 clock cycle to achieve my purpose, 10-bit shifting, right? If it is a 31-bit shift, it will take 31 clock cycle to complete that shift operation. The per cycle 1-bit shift, right? In this structure. Now let us investigate if it is possible to make a faster shift component, like given given some values like the 32-bit or 64-bit. Question is, can we do a faster shifting of the bit in the either direction than using this kind of sequential circuit that we just created? Answer is yes, there it is possible. There is a way, and we call it a barrel shifter. A barrel shifter is a very interesting structure. It has lot of multiplexer. Okay, lot of multiplexers. Like for example, like this is like I believe uh, it can shift this thing, this one, like left shifter and right shifter, these two component I am showing. It can shift up to like 3-bit position, like a value, given value like 4-bit value b0 to b3, you can shift it by 3-bit position, which is okay for 4-bit. Your anything more than 3-bit shift will result in 0, so we don't need it. Now this is for like that 4-bit shifter, which basically has 8 multiplexers. Okay, the basic idea here is, like, if you think as an arithmetic, not arithmetic, I would say bitwise function of shifting, that means you are kind of taking a bit from a bit pattern and putting that bit into some other index, and you are basically operating this uniformly over all the bits. Like, what I mean is that you take a bit pattern, and let's say you take a 32-bit pattern and you want to shift by 5-bit. So what you do basically, first 4-bit you fill up with 0, like LSB side 4-bit fill up with 0. Then the original bit patterns bit 0 will go in a 5th position, right? Bit 1 will go in a 6th position, bit 2 will go in a 7th position, and so on and so forth. So you are uniformly shifting first bit to the 5th position, second bit to the 6th position. So this is you are like shifting by a constant offset those bits somehow, right? And think like these bit patterns you are getting out as an electrical wire signal. Like there are electrical wire, either voltage yes or voltage no, so that becomes your 1 and zeros. Then somehow if you just bend those wires into this 5th position and feeding in that 5th position as at the result side, your purpose is done basically, right? So it's kind of you are picking up a bit from one position and putting that bit into the other position, almost like you are bending the incoming wires into the right position that you want to place it. That's the basic concept of it. Now we'll see how these multiplexers are coming into places. So barrel shifter works in this with this principle. First of all, it shift by stages. Okay, shift by stages. We are taking a 8-bit example here, and so shift left, for example, is by 5 is basically your 5 we can represent as a 1 0 1. Okay. Now the shift amount is broken down in that number of bits, right? So like for example, your 8-bit will be like 3 by 3-bit position. You can express the number of shift amount, right? Just think of, like, for the MIPS processor, we have the shift amount number of bits as 5 because I can shift from 0 to 31. Anything more than that, it will result 0. Now to represent 0 to 31, you need log base 2 of 32, which is 5 bit, right? For 8 bit similarly, you can shift from 0 to 7. So your shift amount will be range from 0 to 7 bit. So you need log base 8, which is 3 bit, to represent your shift amount. Okay, that's why this 3 bit came into picture, right? Now let's imagine we mark them, these 3 bits for a 8-bit shifter, as S2, S1, S0. Okay. You can also think this 101 is we can represent that also, that amount 101 in binary, which is total 5 in decimal. We can break it by its positional value, right? So S2 is 1, which is like represents of amount of 4, like 2 to the power 2. Then S1 is 0, so the positional value was 2 to the power 1 2, but you multiply with 0, that becomes 0. And S0 is 2 to the power 0, and 1 into multiplied 2 to the power 0, which is 1. So you are breaking down the 5 into 4 plus 0 plus 1. So if you want to shift some bit pattern, what you can do, you can shift by 4, then hold that position, then shift another by 1, right? So that's an equivalent operation you can think of. Now with this intuitive breakdown of the bit shifting in its corresponding positional values in the binary, what we essentially doing is that if my corresponding SN bit is 1, I will shift to that side, like left or right. Okay, let's say talk about the left shifter. I will shift left to that much amount. Essentially what I mean is that you are breaking down, or you are representing 5 amount as 101. So I look at the first one, let's say S0 position. If it is 1, I will shift the given bit pattern at this stage with 1 bit. Okay, so your result from this stage will be like 0. We are introducing a 0 on the first LSB side, and then take each bit and shift to its 1 bit left. Okay, and last bit will go out of the scope. The MSB from the original pattern will go out of the scope. Then next S1 we are looking at, that is being 0. So my positional shifting would be 0. There will be no shift. So I will take my next result, next stage result will be like the bit pattern itself, like the stage 1 result. Now S2, if it is 1, my positional breakdown for that bit selection, or S2 bit being 1, would be a resultant 4-bit shift. So what we'll do, we'll introduce 4 zeros into LSB position side, and then take each of the bit from that previous stage, like stage 1, let's call it stage 0, stage 1 and stage 2. Then from the bit pattern we got at the stage 1, the LSB will be shifted by 4 amount. Then next will be shifted by another 4, next will be shifted another 4, next will be shifted another 4, and rest of the 4 bit will go out of the scope. And we have this result, right? We have this shift result exactly. So we started with a bit pattern, then stage 0, we shifted by 1, stage 1 we shifted by 0, because that's what my positional breakdowns are like this, because it's a stage 0 is 2 to the power 0 into 1, stage 1 is 2 to the power 1 into 0, stage 2 is 2 to the power 2 into 1. So positional shifting for each stage would be 4, 0 and 1 respectively. So we have a result here. Like, then let's take another barrel shifter left, another example. Oh, so this one I already mentioned you, like 8 bit needs log base 2 to the power 8, like log base 2 of 8, which is 3 stage shifting. Now another shift by 2, let's say the same beat pattern we want to shift by 2. So 2 in the 3 bit, it is 0 1 0. I am talking about the unsigned representation in the 3 bit. So stage 2's shifting amount of shift will be 0, stage 1's amount of shift will be 2, and stage 0's amount of shift will be 0. That means for this amount of shift, we are going to stage 0, no bit shift, we are take that stage result is same as the original bit pattern, and then stage 1 is a 2 bit shift, so we are shifting 2 bit, introducing 2 zeros at the LSB position, and taking the stage 0's bit pattern and shifting each bit by 2 position, and MSB side 2 bit will be going out of the scope, and then S2 is amount of shifting is 0, so I will take the S1's bit pattern as it is, right? So this is the strategy, and you can well imagine for a 32 bit like value, 32 bit representation, you need log base 32, which is 5 bit 5 stage such operation. Okay, 5 stage of such operation, and that can complete your like 0 to 31 in generic shifting. Anything more than that will result to 0. Now, how do we electronically do it, right? So far we are kind of assuming we are having some like a wire coming out of the bits, and as there is a shift needed, I am kind of bending the wire and putting it in that corresponding shifted bit position to kind of mark, okay, this is what my result is going to be at that stage, and if there is no shift, we are taking that wire as it is on that position on that stage. So we are kind of bending and shifting kind of wire, that kind of concept, but really inside the hardware we cannot do this bending. You can well imagine, right? You cannot just go in the hardware and bend some and tweak some wires, right? So we need to have a solution, and for that we have to use multiplexer. Why? Because see, from one stage to another, right? Let's say stage 0's first bit position, LSB position, the source can be 2 ways, right? One is directly you are coming from the LSB of the previous stage value, or a 0. So there is 2 different source that can come into this stage 0's place, right? For as such, for any bits or the any stage, you have 2 different sources, alternate sources that can come with, right? So it's basically like shift by 5 has this kind of like repositioning of the bit, and shift by 2 has alternate repositioning of the bits. So you have two sources for one destination, and you know exactly how to select, right? If there is no shift amount is 0, then I take the green path, right? And if there is some shift, I will take the red path. So that means it calls for a multiplexer, right? We need to select whether I want to shift or no shift at that stage. So that's where the multiplexer comes in. So you have, for 8-bit, you have 3 stages. Each stage has 8 multiplexer. So 24 multiplexer in action, where your S0 is coming from your like shift amounts, bit positions, right? So shift amount is like for shift 5 it is 101 on the S21, S10, S01, and shift 2 would be your S20, S11, and S00. So, and you are connecting those signal to these alternate terminals like 0 and 1, 0 and 1, based on if S0 is 0, that means I am shifting. So my output from that stage will come from through my red path, right? And if it is 0, then output will come from the green path, which is copying the bit itself onto the next stage. So this bit from the original bit pattern will follow through this mesh of multiplexer, and ultimately at the output stage it become your shift result, okay, by this right kind of selection of shifting, okay. And amount of shifting that a part stage is dictated by previous stage output or previous stage bit going to which position. It is just by the positional connection, that's all. So you are making a wire connection from this last like second stage multiplexer output to the third stage multiplexer output at a different location, and by that amount of bit shifted. So this is what is the barrel shifter is, right? Now with this, there is no way I can do with this circuit, right? The one I'm showing, it is only for the left shifting, right? That means I have to have something for the right shifter as well. So right shifter would be something like this, right? Right shifter would be something like this. That means each of the bit position now have 3 potential sources, right? 3 potential sources. But let's say this I'm just constructing just right shift only parallel shifter. So I will still have 3 stage. Each stage has 24 multiplexer, and just by connection, how I'm connection making from the source stage into the first stage multiplexer, through the second stage multiplexer, through the third stage multiplexer, I am keeping on shifting those bit with that target amount. So now this is both way, right? Remember, like this, a source for, now this guy is what I'm trying to show here. It is not, it is falsely written as a right shifter, but it is what I'm trying to show you, that on top of that we have the left shifting as well, right? So this becomes a very complicated data source and target, and we need to have, as I mentioned, right, each bit from the previous stage can potentially go 3 places, right? Either some bit left or some bit right, or straight at that position. So we need to have some complicated structure there. So that's why, and with that it will also also there would be some kind of selection whether I'm doing a left shift or right shift, depending on that which path I will take. So some additional complexity on this top of this multiplexer. So In order to keep our life simple, we don't do this. We separately construct right shifter, which has like for this case 8-bit case, we have 24 multiplexer in the right shifter and 24 multiplexer in the left shifter. Okay, so let it compute both the result. What you all need to do, just pick up the right result depending on what shifting I am looking for, right? So I'm sending a data, sending the shift amount, which is 3-bit, and LNR. If this guy is 1, that means I want to do left shift. If this guy is 0, I want to do a right shift. And then I'll select through another 2 by 1, 2 to 1 8-bit multiplexer. So 8-bit, we are selecting between either right shift answer or left shift answer, and that becomes my ultimate output. So as a result, like if I make this guy as a black box, so what all you are giving to this source, this component, as your data 8-bit, your shift amount 3-bit, and you are telling whether you want to do an left shift or right shift. So with this, there is no clock involvement. So this thing is much faster on average than a sequential shifting. Okay. Now, why I'm saying it is on average, like you can think like the flip flop, the shifter with the flip flop, minimum it takes a 1 clock, right? 1-bit shift. If no shift, nothing needs to be shifted, right? And maximum it will take 31 clock for a 31-bit shift, right? So you have a time period, per clock. So you can say that my worst case, it will take 31 into time period of the clock, that much time to shift. Best case, it will take time period, right? That amount of time to shift, complete the sequential shifting. Now, how much this takes? Remember, these are all complex combinatorial circuits, right? And it has itself multiplexer inside, has its decoder and selection logic and all this stuff, right? So it is a series of stages you are coming through, and each stage will add up some physical delay. Remember, these are all electronic component. No electronic component compute like instantaneously result, and it's not that as soon as you place your order into this barrel shifter, immediately you get the result from it, right? All these combinatorial stages will need some delay, will introduce some delay and need some time to process that result. So we really need to see that how much time it is needed, right? It is a constant, by the way. Unlike sequential, it may take a 1 cycle versus 31 cycle. This shifting, barrel shifting, combinatorial shifting is a constant time. We know that, right? Then you need to see, like, this is a constant time delay. I know how much time it takes, this shifter takes to produce a result. And then you average out your sequential shifter's performance, right? In the lifetime, it will shift random, like let's see, 0 to 31 or more. It's kind of equally likely, and we can compute that probability, right? How much it will shift by 1, and in this lifetime, and how much it will shift by 31. And if you kind of average that out, let's say is a 16-bit shift lifetime, right? So let's say it will take 16 multiplied by t is being time period. In the average shift operation will take that much time. In that case, you need to compare the combinational delays you are coming out of the barrel shifter with that 16 multiplied by time period of the clock, and check which one is faster for your given circuit or given scenario. Then you choose your sequential circuit or a barrel shifter. Okay, so for the performance improvement, it is not that always that combinational circuit will actually does it faster. It really depends on your use cases. You need to do some right analysis at that point. Okay, but my claim in general, barrel shifter work faster than the corresponding sequential circuit. All right, but it's a huge circuit. It takes a lot of components there. Okay, so its cost, like if you think of like component cost wise, barrel shifter is costly element. Okay, so people doesn't use it often because of its cost. Simple, right? Only it puts it them in a critical component of a system so that it can achieve a faster result. All right, so that's all for this lecture 8. If you have any questions, send me email or ask me in the class.